after 11:30 or 14:30. Okay. Anytime.
All right. So let me begin with a word of prayer. I'll start. Heavenly Father, we thank you for this day. Again, I thank you for the students. Just ask you to guide our steps today. Help us to glorify you what we do and to understand a little bit more about the nth order linear ordinary differential equation problem. Lord, in your name I pray, Lord Jesus. Amen. Before I forget, here is the attendance sheet. If you want to add a date to that, that'd be awesome. Thank you, thank you. Of course, I also have your handy dandy top hat code over there. So, what is a linear nth order ordinary differential equation? So here, we've, for the most part, up to now, only talked about constant coefficient differential equations, right? And only order 1. But the nth order linear differential equation has the following form. So definition, if a sub n minus 1, a sub 1, a sub 0 are given functions with, real valued. And then an, let's see here, let me use prime notation here. An, the nth derivative at, let's say, t, plus an minus 1, the n minus 1th derivative at t, plus plus, let's say, a2, y prime prime. I guess I'm writing the t dependence here, so let me, oh goodness gracious, t plus a1 y prime of t plus a sub 0 equal to g is an nth order linear ordinary differential equation. Now here I'm assuming that the a sub n is non-zero, all right? So it's like a non-zero function. And typically, the given functions, have some sort of common domain. So you could say the domain of definition for the differential equations, like all possible t, that, are in the common domain of all the coefficients here. These given functions, these are the coefficients of the differential equations, right? These are coefficients. You can say they're coefficient functions. Now, a lot of times, the coefficient functions will just be constants. In that case, if all the coefficient functions are constant, it's called the constant coefficient linear ODE, right? We know the most about that. Now, I've written it for the independent variable being t, right? But like alternatively, we could have like, an, and I could write it in different notation, right? I could write the nth derivative of y with respect to x, an minus 1, the n minus 1th derivative of y with respect to the x, and so forth. D squared y dx squared. All right. A1 dy1 dx, not dy, just dy dx, plus a0. Ooh, I forgot something. Oopsie. There's supposed to be a y here, equals to g. So the equation above isn't quite right yet. I'm missing a very important y right here. And I seem to have numbered this y, which is bogus. That's just a y. I don't know why I'm putting a 1 there. Dummy. Me, not you. So this is supposed to be a, not y. All right. This is a linear. So the reason it's linear is both y and its higher derivatives all just appear in a linear fashion, right? There's no square of y. There's no square of y prime, anything like that. And let me suggest yet another, even better notation for the linear nth order ODE. So we can use what's called operator notation. So let d equal to the derivative with respect to x, for instance, right? Then we can use this notation, like dk acting on y. That's a fancy way of writing, the kth derivative with respect to x, right? And if we use that notation, then we can rewrite the differential equation we're talking about as like an d to the n acting on y plus an minus 1, d to the n minus 1 acting on y plus dot 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 a2 d squared acting on y plus a1 d acting on y plus a0 times y equals to g, right? So, again, yet another notation. Yet another. And finally, probably the best notation is to factor out the y, right? We can actually look at this all together as one single operator, an d to the n plus an minus 1 d to the n minus 1 plus dot 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 a2d squared plus a1d plus a sub naught, all of that acting on the function y gives me back the function g. All right. So our typical notation in here is to call this all together collectively L. The L is for linear, all right? So in other words, what I'm saying is that I can trade this differential equation and I can write it instead simply as L of y equals to g, right? Where L is the differential operator an d to the n plus dot 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 plus a1d plus a sub naught, all right? Now, I will talk much more about the theory of operators like next time, or perhaps at the end of class. My main focus today is to explain to you the theory of the nth order problem and tell you what it is that we can expect and what the structure is that we can expect. We have some concepts and new ideas we need to learn along the way, like what does it mean for functions to be independent, what's a solution set, what's a general solution, all these things. But just a little bit of a preview for once we get past that is ultimately we want to understand what the structure is of these this kind of operator. And I'll just give you a spoiler. The main thing is we'll be able to see. You can see this already. This is a linear operator. And what that means is that it has the following property. If I take L of like C1y1 plus C2y2, that is actually C1 L of y1 plus C2 L of y2. This defines linearity. Now, I should be more careful here. Oh, no. I was about to say, well, that's not... I was about to worry myself that, there's a g. See, if that g is non-zero, right, then... Well, I need to complete the thought here. But it is true, nonetheless, that this is, in fact, a linear operator. Because differentiation is linear, second differentiation is linear, third differentiation linear, and so forth and so on. And if you add together linear operations, you get a linear operation. All right? So it is true. So I guess, elementary theorem I probably could do right now before we do anything else is that if we had L of y1 equals to 0 and, L of y2 is equal to 0, then L of cy1 plus cy2 is equal to CL of y1, right? Plus C2 L of y2, which is what? 0, right? In other words, the sum of, well, I shouldn't say this, it's not just the sum, the linear combination of homogeneous solutions is a homogeneous solution. Now, I just showed you the proof for two of them, but it would still be true if we had like n of them, right? If I had the sum I equals 1 to n of like ci, yi, I would still have the same argument going through. The sum of, the linear combination of homogeneous solutions is still homogeneous. All right? And so our goal, right, is to learn how to solve L of y equals to g as best as we can. We want to solve this problem. I suppose before I get too far into the theory, it would probably be helpful for me just to give you an example, right? So here's a simple example that we can all solve together, right? Suppose you're calculating the nth derivative of y equals to e to the x. Can we solve this differential equation, right? It is an nth order differential equation, so like, what's the solution? If you integrate both sides, what do you get? What happens if we integrate both sides? What do we get? Right? Integrate both sides. The nth derivative is the derivative of the n minus 1th derivative, but the integral of the total derivative is the thing again. So we have n minus 1th derivative of y is e to the x plus c1, right? Integrate again. We get dn minus 2y is equal to e to the x plus c1x plus c2. Integrate again. We get dn minus 3, can't write, dn minus 3y is equal to e to the x plus 1 half c1x squared plus c2x plus c3. If I integrate again, you see where we're going with this, all right? So I'm just going to get to the end of it. Eventually we get to y is equal to e to the x plus what? What happens as we integrate? You can kind of see the pattern if you just think about like 3 derivatives. That's probably enough to see the pattern, right? 3 derivatives, if I integrate 3 times, I'm going to pull down a 3 times a 2. So I have a 3 times, I got a 1/6 on the leading term. But in this n-fold one, you'd have 1 over n factorial c1 x to the n. And then plus 1 over, n minus 1 factorial c2 x to the n minus 1. And then so forth and so on down the line until eventually we get to cn minus 1x plus, cn. So this particular problem is pretty nice because I can just integrate it repeatedly to solve it, right? Wouldn't it be wonderful if we could just solve every differential equation this way, if it's just a matter of just repeatedly integrating? It kind of is, right?
Can that 1 over n factorial go into constant c1 or no?
I suppose it, so you're like, can't I just, or if you'd rather, you could say the solution has ex plus like, let's say b1 x to the n plus b2 x to the n minus x minus 1. Eventually I get to like bn minus 1x and plus bn, I guess. Is that my numbering? Numbering consistent? I hope that numbering is consistent. It might not be. I think it is. I've got n constants. I should have n constants in the solutions from the n integrations it took to solve for y, right? But yes, you could relabel the constants, absorbing the factorials, the fractions into it if you don't care about those. It's fine. I just was leaving them there just to show you we literally are just integrating at n times. Now there are precious few differential equations I can just directly solve like this. But this already shows you the general structure that we're going to prove exists today. All right? Because what's going on here, and thank you for relabeling it in a prettier way, I like that. This right here is what we'll call the homogeneous solution. Or I could just call it y sub h. Notice that d, oh man, I didn't do it. So that was supposed to be n minus 1. I knew I did something wrong here. I shouldn't get yn, right? Like, for example, let me drop it back a second here. Y prime prime equal to 0 would give us what? C1 y equals to like C1 plus C2x, right? So I should have one less degree than I shouldn't have gone all the way to n. I should go to what? Like, this should be n minus 1. And, rats. I'm sorry, guys. I was trying to be accurate, and I should have just done what you suggested. I should have just written that down. I wouldn't have been wrong if I did that. But I tried to do the details, and as such, I messed it up a bit. So it should have been n minus 1 factorial, like that, and then down. Eventually, you get to C1 like that. So sorry about that. I mean, you can see it here already. So like, I don't have, look at this. If I differentiate this n-fold times, it doesn't go to 0, does it? What happens if you differentiate x to the n n-fold times? You don't get 0, you get n factorial, right? So I have to have an n minus 1 here. And n minus, so it goes n minus 1, n minus 2, all the way down to 0 like that. But if we did that, then if you calculate the nth derivative of the homogeneous solution, you get 0. On the other hand, the other piece here is what we'll call the particular solution, yp. If we calculate the nth derivative of the particular solution here, of course we just get e to the x again. And so you see that the general solution is the form, it's the sum of the homogeneous plus the particular. This is the so-called general solution. And also in this example, just to finish illustrating the ideas we're going to talk about more systematically here, the fundamental solution set for this problem, they are 1, x, x squared, all the way up to x to the n minus 1. Those are functions whose linear combination forms, those functions, their linear combination forms the homogeneous solution. Okay? So, yep.
Not a silly question, but I'm trying to track your process there. What happens to the b, like the n minus 3, when you derive it 3 times? It just disappears. Is it because it gets too small and just goes away, or?
Well, eventually you get to the 0th derivative, which is by definition just the function again. So like eventually n minus whatever becomes just y prime, right? And when we integrate y prime, we're just back to y. So like the next to last, before the last integration, we have reached y prime equals to stuff. Then we integrate both sides. We just get y equals to the integral of the stuff. So, yeah. Now, I won't go through the details, but if you look in the chapter 1 notes, I derive by something called reduction of order, right? I derive that if you have, like y prime prime plus y equals to 0, that implies that y is equal to c1 cosine x plus c2 sine x. And through a similar derivation, you could solve y prime prime minus y equals to 0. That actually implies y is equal to c1 cosh x plus c2 sinh x. Of course, both of these, I'm assuming what? I'm assuming y prime is like dy dx, right? So I'm not explaining to you why at the moment these are true, but I'm just saying if you look back at the first order chapter, at the end of that, I showed that you can use reduction of order, and by doing an integration and about a page of calculus, you can derive that the solution to y prime prime plus y equals to 0 has this form in general. All right? So these are both homogeneous equations. And in this case, again, we see that the solution is a linear combination of two functions, cosine and sine, or for the second one, cosh and sinh. And so this is generally going to be the pattern we're going to look for. We're going to look for finding n functions which we can form the homogeneous solution set to an nth order problem. All right, so again, I'm mostly focused on theory today, so let's get to it. So here's theorem 3.1.2. So we have, suppose A0, and so I'm going to try to like the theorems as I have them stated in the notes. I'm not like, I don't like the numbering, so I'm going to try to fix it as we go in here, guys. Because like essentially my numbering in the notes, I have like the enumeration flipped from like what I want to write, and I'm just going to write it correctly on the board, hopefully. So suppose that all of these are continuous on an interval I, which is a subset of the reals, all right, with a sub n of x not equal to 0 for all x in the interval, all right. So we're supposing that the leading coefficient a sub n is not equal to 0 on the whole interval, which is the domain of definition here, all right. Then if you give me a point in the interval, let's call it x naught, and any set of n constants, which we're going to call y1 through yn, all right, then this theorem says that there exists a unique function, phi, which solves this differential equation, all right. So here's the deal. Then, given any x naught in the interval I, and y1, well, I guess I numbered them y0 through yn minus 1 in the reals, all right, there exists a unique function, let's call it phi, such that two things hold. Number one, a sub n of x times phi times the nth derivative at x of phi plus an minus 1 of x times the n minus, there's supposed to be parentheses n minus 1, the nth minus 1th derivative of phi at x plus dot 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 plus a2 of x phi prime prime of x plus a1 of x phi prime of x plus a0 of x times phi of x equals to f of x for all x in I. Let me give you a very much easier way to write that, right? If we use the notation I introduced at the start of class, how can we express this more compactly? Like, what's another way to say all this? AKA what? L of phi, right, is equal to f on I. Assuming that I define the differential operator using these continuous coefficient functions that I'm assuming exist in this theorem, all right? So I'm saying that, number one, if they're continuous on an interval I, and the leading coefficient of the operator is non-zero, there exists a solution to the problem. That's great. But it's more than that. How about these numbers over here? What do these have to do with anything? Number two, how do those numbers figure in? Phi of x naught is equal to y naught. Phi prime of x naught is equal to y1. Phi prime prime of x naught is equal to y2, and so on down the line. Eventually we get to the n-1th derivative evaluated at x naught of this function, this solution, and it's equal to yn minus 1. So in words, that is to say, phi solves the nth order initial value problem at x equals to x naught. I like to write IVP because it doesn't give me joy to spell initial value problem. So IVP, initial value problem. Right. So this theorem says that if you have continuous coefficients and the leading one is non-zero, there exists a unique solution to any initial value problem. All right? And the reason there's going to be more than one solution to an nth order problem is because there's an infinity of different choices you can make for these initial values. Right? Like these second order problems I wrote, example 2 and example 3, you need two initial conditions, essentially because a second order differential equation involves essentially like velocity and acceleration, right? So to fix it, you need a position, an initial position and an initial velocity to fix a specific solution. So unless you know an initial condition and an initial position and an initial velocity, you don't have just one solution for a second order problem, right? For an nth order problem, to find a specific solution, we're going to need not one, not two, but n initial conditions to fix a specific solution. But this is very encouraging because it says that there's hope. We can do it every time, as long as the coefficients are continuous. All right, so there's that. That's the theorem. Now, don't worry, I'm not going to prove the theorem. I'm just going to state it. Next up, we need to talk about, oh, did I ever move the camera over there? Oh, I'm my own worst cameraman some days. See, physics yesterday lulled me into a false sense of security because they had been moving the camera around for me, and then I had the misfortune of putting it in front of a student who wasn't thinking that he should move it. And that's fine, because I didn't ask him to, in fairness, but he didn't, and then I thought he was, and then it's like, oh man, and I did a really good example too in the middle board. I don't often say that, but it was a good example. So, next up we need to define linear independence of functions. What do we mean by linear independence of a set of functions? Do you guys want to tell me? Look it up on Google. I mean, you could do that, I suppose.
Linearly independent, meaning that it's not dependent on.
It's not dependent. Yeah, maybe. How about this? Can you guys give me some examples of functions which would be linearly dependent, like the opposite? Like, what are we trying to avoid? How about this?
Well, I think of linear independence and dependence, I think of matrices.
But we're talking about functions. So, you know, for functions, how about this? If I had like y1 is e to the x and y2 equals 2e to the x, you'd be like, well, those aren't really different functions, right? One's just a multiple of the other, you know? Or if I had another example, if I had like y1 is e to the x, y2 is e to the minus x, and then my y3 was like, I don't know, 2 cosh x or something, right? Well, 2 times cosh of x is what? It's e to the x plus e to the minus x, right? So that's equal to, y1 plus y2 in my discussion. So those are not independent, right? Because the third one's just a sum of the first two. And So the key feature here, though, if you look at this, the way we look at it is this. This would mean that we have y1 plus y2 minus y3 is equal to 0. This, exemplifies linear dependence. So what if we don't want that? So here's the definition. y1, y2, yn are linearly independent on I, a subset of the reals, if and only if c1y1 plus c2y2 plus plus cnyn equals to 0 on I implies c1 equals to 0, c2 is equal to 0, cn equals to 0. Now when I say on I, understand that this is an equation about functions. It's an equation about functions. So to be more expansive about what I mean by that, let me write down the following equation. What I'm saying by this is I'm saying that like c1 y1 of x plus c2 y2 of x plus plus cn yn of x is equal to 0 for each x in the interval of consideration. So when we talk about linear independence of functions, we have to talk about linear independence of functions with respect to an interval, all right? It's possible for some functions to be linearly independent with respect to one choice of intervals, but to be linearly dependent with respect to a different choice of interval, all right? You want to see that? I can show you real quick. Like, see this? If I have y1 is equal to x, and if I have y2 is equal to the absolute value of x. If this is the situation here, if I say, y1, I can say y12 is linearly independent on the reals, but y1, y2 is not linearly independent on, let's just say, the positive reals. Because on the positive reals, those are the same function. But on the totality of the real numbers, they're not the same function. Right? Two functions are linearly dependent if and only if you can write one as a scalar multiple of the other. Right? And I cannot write absolute value of x is just equal to a constant times x on all of the reals. Because the quote-unquote constant I need is 1 for positive, and it's minus 1 for negative, and that is not a constant, all right? So this is the idea. We want independence of functions. Okay, so suppose we have this, right? Let's add an additional proviso here. Let's make an additional provision. Let's assume that we can differentiate these functions, right? If you can differentiate these functions, if this is true for all x, we can differentiate it, right? What happens when you differentiate this? If you don't mind, I'm going to stop writing the x dependence because it's really annoying. Most of you are just like, it's just you writing, so whatever, right? It's fine. That's why I type notes. And as long as you understand. Then what? We can do what? We could differentiate again, right? And we can keep doing this, right? We can keep differentiating these equations until we get how many? N of them. That's a good idea. Why would we want n equations in n unknowns? These were C1s. I keep changing the numbering on the first one. I'm an idiot. So eventually we get to the n minus 1th derivative. All right. And then we have, at this point we have n equations in n unknowns. What are the unknowns? Those are the constants, so C1, C2, Cn. If these are linearly independent functions, what is the condition? We must have, if you have the first equation, it must imply what? It must imply all of the constants are 0, right? We can't have this situation. See here? This is C1 equals to 1, C2 equals to 1, C3 equals to minus 1. Those are not all 0, despite it being a trivial combination. Do you see? So we're trying to avoid that. So we need the situation that if you take a linear combination of all the functions and set it equal to 0, it must be the case that all of the coefficients are 0. All right, that gets us independence. So if you take this and you rewrite it as a matrix equation, all right, we can rewrite it like this. We've got y1 of x, y2 of x, yn of x, then the second row, y1 prime of x, y2 prime of x, yn prime of x, second row, and this goes on. Eventually, the last row, we get y1, the n minus 1th derivative of x, y2, the n minus 1th derivative of x, of y sub 2, and finally the n minus 1th derivative of the nth function of x, like that. This is an n by n matrix of the first row is the given functions, the second row is the derivatives of the function, and so forth and so on, until the last row is the n minus 1th derivative of the functions. All that times what? This times it has to be equal to 0, right? But this is C1, C2, Cn, all right? And that's supposed to be equal to 0, 0, 0. There are n zeros here from the n equations. We can rewrite n equations in n unknowns, if they're linear, as a matrix vector problem. All right? Now, I'm not going to prove this in here, but I'm going to tell you from the theory of linear algebra, if the only solution to this is the 0 solution, that forces me to say something about the coefficient matrix, which is what? So, by the way, this is called the Wronskian. Well, this is not yet the Wronskian. My bad. Let's just call this the matrix A. Needs to be what? If this has to tell me C equal to 0 is the only solution, there's different ways we could look at it. The one is that A is an invertible matrix. All right? That's of some use to us. More to the point, A must have non-zero determinant. If this only has the 0 solution, the theory of linear algebra forces this to have determinant non-zero. All right? So, for this reason, we define the so-called Wronskian of n functions. The Wronskian of n functions is simply the determinant of the matrix that I just found right there. And the theorem that this calculation shows you is that if you have n linearly independent functions, right, then the Wronskian of those n linearly independent functions must be non-zero. So Wronskian of y1, y2, yn at the point x is equal to the determinant of like y1 of x, yn of x, y1 prime of x, yn prime of x, and so forth and so on until you get to the n minus 1th derivative down here. And now I'll actually do, we'll calculate this for a set of functions here in just a second. But this is the so-called Wronskian of y1 through yn. And the theorem that follows immediately from the calculation we just did is that, I'll take your question in just a second here. If y1 through yn is linearly independent on I, then the Wronskian of y1 my n at x is not equal to 0 for all x in I. Yes, sir.
Yeah, where's the semicolon in the definition?
Oh, I'm just distinguishing the last thing from the first.
Okay.
You could put a colon there if you want. I mean, different people do different stuff. You could put a slash. I mean, whatever, just something to distinguish. See, the last point is the dependent variable, whereas the first bunch were the, you know, whatchamacallit, the functions we're judging the linear independence of, all right? So, so let's see here, for example, I'm going, what, example 4? Let's try something here. How about y1 equals to 1, y2 equals to x, y3 equals to x squared. Let's see, and we'll let the interval just be all reals, all right? Let's judge, are these linearly independent functions? Okay, we'll use the Wronskian. So we're going to calculate the Wronskian of 1, x squared, all right? And I guess I'll do it at x. It's kind of funny. So here we go, determinant. We put 1, x squared for the top row, right? Then I differentiate. What's the derivative? 0, 1, 2x, all right? And then what? 0, 0, 2. All right, great. Now, I don't know if you guys know determinants or not. If you don't, look at the notes. I give formulas, all right? This is that thing you did for the cross product in Calc 3, right? But there you had the I, the j, the k in the top row. But it's the same pattern. So like but here's a fun fact. If you have a triangular determinant, right? Because I've got the zeros down here, there's a shortcut. We just multiply the diagonals. So you want to know about that shortcut, right? I mean, yeah, definitely. So this is 2, which of course is not equal to 0. Thus, 1x squared is linearly independent on R. Now, the Wronskian is one tool we can use to detect linear independence. We can also go back to the definition. Like for two functions, there's kind of an easier way to do it. You know, like I said, for two functions, they're linearly dependent only if one's a multiple of the other, you know? So sometimes for like two functions, there's an easier path. Let me just take a second here and show you for two functions. Let's work on something. How about, suppose we have like e to the alpha x and e to the beta x for alpha not equal to beta, right? And our interval of consideration, again, will be all real numbers. I'd like to show you that these are linearly independent, okay? So one way we could do is just to calculate the Wronskian, and we'll do that. So the Wronskian of e to the alpha x, e to the beta x at x would be equal to the determinant e to the alpha x, e to the beta x. All right, now I need to differentiate those. How do I do that? Chain rule, right? Okay, so what is that then? So alpha e to the alpha x, and by same token, beta e to the beta x, right? So the determinant of a 2 by 2, we multiply the diagonals. I've forgotten how to say diagonal apparently. E to the alpha x, e to the beta x. And then I subtract the off diagonals product, which is alpha e to the alpha x, e to the beta x. Now we can simplify that. That gives me beta minus alpha times parentheses e to the alpha plus beta times x. Good news, the exponential is what? It's what? It's positive, right? Yeah, so this is non-zero, and what do we know about beta minus alpha? We assumed what? they're not equal, so that's also non-zero, right? So this is not equal to 0, thus e to the alpha x, e to the beta x, linearly independent on the reals. An alternative argument that I could give here, right, which I'm going to do in red over here. Another way you could have argued, cut myself out a little cutout here, if e to the alpha x is equal to a constant times e to the beta x, right? Then what? That would mean that the constant is equal to what? Constant's equal to e to the alpha x divided by e to the beta x, right? Which is also known as e to the, alpha minus beta times x. But this is absurd, because e to the alpha minus beta times x is definitely not a constant, right? If you don't believe me, how would you prove it's not a constant? What would you do? What defines a constant in terms of calculus? Its derivative must be 0, right? If I differentiate that equation, I get derivative of k is 0, but the derivative of the other side is alpha minus beta times e to the alpha minus beta x, which is decidedly non-zero, which gives you something 0 is equal to something non-zero, which is, of course, an absurdity. I don't require you to write all that. To me, this is enough. I go, okay, this equals to that, which is impossible. Thus, no such k exists, right? So if no such k exists, then again, that implies that e to the alpha x and e to the beta x are linearly independent, all right? Let's see here. Example 6, thank you. How about if we have like y1 is e to the lambda x and y2 is x e to the lambda x. Can you guys, how would you prove those are independent? I mean, you got kind of two choices, right? We could either use the Wronskian, we could use our Wronskian business, we could use the Wronskian to calculate that and show that it's, non-zero, therefore linearly independent. Or what can we do? Yeah, we could divide one by the other and show it's not, constant. So, like if, y1 was equal to a constant times y2, that would say that e to the lambda x is equal to a constant times x e to the lambda x, which is to say that 1 is equal to kx, right? So which is to say that the constant is equal to 1 over x, which is dumb. All right, it's dumb. So no such k exists. Thus, y1 e to the lambda x and x e to the lambda x are linearly independent.
So really,
And I should say on the real numbers, right? So
if we get something in that structure where basically we have the same equation, there's just a k in front. Well, would technically, because x wouldn't be considered, okay, that's the x variable. But you're assuming a constant.
well, there's a theorem. The theorem of linear algebra I'm using is that two functions are linearly dependent if and only if one of them is a scalar multiple of the other. So I'm going back to rest on that lemma. So if you'd like to see it proved badly, if you look at my 221 class from earlier this week, I spent about 10 minutes getting confused about it. So I'm not going to prove it here because No, it's just true. And it's kind of obvious if you think about it. If you have two things, the only way one can be dependent on the other is if they're multiples of each other, right? It's more complicated if you got three things, but for two things, it's just that. Of course, we could also calculate the Wronskian. All right, so next up here, I have theorem and some of the proofs in here, I mean, there is, I will give you guys homework problems where I ask you to, prove or disprove the linear independence of some given set of functions, right? So you got options, right? You can either try to calculate the Wronskian, or you can, use the kind of arguments I was just giving. Alternatively, you could just try to solve the equations I just erased directly. I do that sometimes. If you can, set a linear combination of the functions equal to 0 and prove that the constants are all 0 by the algebra and the calculus of the problem, that's another path, right? You could just go back to this system and just do calculation on it directly to prove that those constants have to be 0. That's pretty easy with, like, if you think about this problem, for example, if you have ax plus bx plus cx squared equals to 0, can you, and that's true for all x, can you show that a and b and c have to be 0? It's pretty easy to do that. You just plug in 0, it gives you a is equal to 0. Differentiate, plug in 0, it gives you b is equal to 0. Differentiate 2 times, plug in 0, it gives you that c is equal to 0. These calculations I'm talking about, you saw when you studied power series in calculus 2. But that brings me to my next theorem here. So this is the Wronskian on a solution set. Of a linear ODE. All right. So suppose L of y equals to 0 defines a linear nth order is a linear nth order ODE. All right. On an interval I, and y1, y2, yn are solutions on I. All right, period. If there exists x naught in I, such that the Wronskian of these solutions at x naught is not equal to 0, then y1 through yn is linearly independent on all of I. On the other hand, however, if there exists x naught in I such that the Wronskian at that point is equal to 0, then the set of solutions is linearly dependent. All right. So the difference between what I'm writing now and what I had erased is like what I wrote down to start with was just the definition of linear independence of a set of functions. It had nothing to do with a given differential equation, right? In fact, these examples I just did, they don't have anything particularly to do with a given differential equation. I just pulled some functions out of the air and we studied their independence, right? Now it turns out these are actually all solution sets. to differential equations. But if you have a set of functions which is not a set of solutions to a linear differential equation, the way the Wronskian behaves is a little bit different. In this context, the Wronskian has a special structure that's given by this theorem that you don't need to check for all points. It suffices to show that it's non-zero at one point. In other words, non-zero at one point means non-zero at all points for the Wronskian of a solution set. This is a little bit surprising. And the proof of that is actually accessible. We can all do it together. And I put this on, this is a proof I've asked students to do on tests before, and they have done it with success. So let's look at it together. Now, the proof that I would ask of you would not be the nth order problem. That would be, I'm not a monster, all right? I wouldn't do that. N equals to 2 we can do together. So let's look at the n equals 2 version of this theorem. All right, so n equals 2. So what we're up against is a2 y prime prime plus a1 ay prime plus a0 y is equal to 0. We're studying the homogeneous second order problem, all right? And I want to suppose that I have, two solutions, right? That's the data here. Suppose you have two solutions. So we have not just, so let's suppose we have two solutions. What would that mean? If I put a j here, right? I let j equals to what? 1 and 2. I have two functions, y1 and y2, which solve this given second order differential equation. All right? Now I want to calculate the Wronskian for these two functions. What's the Wronskian for these two functions? Because that's what captures their, linear independence. So what is this equal to? Okay, yeah. So yeah, we have y1, y2, right? y1 prime. There's just two functions though, right? And it's second order, so it's a 2 by 2 matrix. This is the Wronskian in the 2 by 2 case. So we have the determinant of this 2 by 2 matrix, which is simply like y1, y2 prime minus y1 prime, y2, like that. Now, I'm about to derive a formula for the Wronskian, so it's helpful for us to take like a much less cumbersome notation for W than like the Wronskian. We're going to just call all of this for the sake of like not writing this mess a bunch of times. Let's just call this W for Wronskian. So the formula we're up against here is, I never moved the camera. W equal to y1, y2 prime minus y2, y1 prime. I'll fix it. It's cool. I don't think I moved it. I might have moved it. I don't remember. Oh, I did move it. When did I do that? Oh, well. I wish I could remember things. That'd be nice. So then what? Well, all right. So my claim is that we're going to find a nice formula for the Wronskian. So what should we do if there's any hope for that? I hope you guys don't mind if I'm going to erase that and just put not linear independent here. There, okay. How about this? If we differentiate the Wronskian, W prime, what's that give me? That gives me W1 prime, y1 prime, y2 prime, plus y1, y2 prime prime, bless you, y2 prime, y1 prime, minus y2, y1 prime prime. By the what? The product rule. That's wonderful, because this and that, they'd be canceling, right? They'd be canceling. And on the other hand, we've got, all right, what we got? We got dw dx, the derivative of the Wronskian, apparently is y1 times y2 prime prime, right?